Hello everyone, welcome back. So today let us start GSW FHE scheme. Then we'll extend it to multi-key GSW FHE. Okay. So why the name GSW? Because it was founded by Gentry and Sahai and Waters. In this case, the cipher text are matrices and homomorphic operations are simply matrix addition and matrix multiplication, which makes this more efficient, this scheme. The basic idea comes from and this was given in 2013. Okay, so the idea comes from the nice property of eigenvectors of matrices. There is a very nice property of eigenvector of matrices. From that, yeah, so the basic idea was to use eigenvector. Now let us see how does they use it. Suppose if we have two matrices, we have two matrices, say C1 and C2 have same eigenvectors. Suppose have same eigenvector V for certain y eigenvalues, for certain eigenvalues m1 m2 respectively. Okay, then the following hold. This V is an eigenvector for C1 plus C2 for eigenvalue m1 plus m2. That means same eigenvector works for the eigenvalue m1 plus m2, and V is an eigenvector for C1 C2 for eigenvalue m1 m2. What do you mean by this? That means same eigenvector can work for the product, which is very fascinating, correct? So this looks like homomorphic properties we would want for the cipher text C1 and C2, and the message is M1 and M2 encrypted under V. Okay, but unfortunately we cannot use exactly this setting, because for a given matrix it is easy to find eigenvectors and eigenvalues. Okay, for this scheme, instead of the secret key being the actual eigenvector, an approximate eigenvector is considered. Instead of the actual eigenvector, we are going to use approximate eigenvector. Okay, for example, say C1 into V, it will be some M1 into V plus some error, correct, for certain small error, and such that this C1 into V, which is approximately same as your M1 into V. And if the ciphertext are added, C1 and C2 are added, then that can again have the error say E1 plus C2. For example, if I'm having C1 plus C2, just multiply it with V, you'll be having C1V plus C2V, which is equal to M1 plus M2 V plus E1 plus E2. This is the error term you are having. You just have to again restrict the error. See, all the FHE schemes have the same idea that if you are able to restrict the error, then you can form a FHE scheme. Okay, so which will decrypt correctly if the original error E1 and E2 are small enough. So what about multiplication? If I'm having C1 into C2 multiplied with V, I'll be having this part. Just if you try to observe it, it is M1, or first it will be first going with the C2. So it is, let me write C1 into C2 into V. So C1 into, what is C2 into V? It will be M2V plus some error E2. Correct. Now if you multiply with C1, you will be remaining with, say, and I'm writing directly M1 M2V plus M2E plus C1 into E2. Correct. So now do you see the error part? It has one term of ciphertext also, which in this situation is quite different. Whereas in the earlier case it was just error, that was okay, but now because of this guy I'm having trouble. So the new error also depends on the message and ciphertext. For the message we don't have any problem because here we are encrypting only zeros and one. Okay, so whereas this does not happens with this guy because your ciphertext might have large entries. Correct. Ciphertext might have large entry, so this is the problem for us. So to ensure the entries will be small and thus error does not grow too error does not grow too much, a gadget matrix is introduced. Gadget matrix is used. Yeah, to ensure the to ensure the entries will be small. So I just wanted to make the ciphertext C1 should have small entries, then this won't trouble me. Correct. To ensure the entries will be small and their error does not grow too much, a gadget matrix is used. So what is a gadget matrix? Yeah, so what is the gadget matrix? Let us see. Gadget matrix G, say that is belongs to ZQ M cross N, and corresponding inverse transformation with G inverse. So G inverse actually what it does, takes the element from ZQ cross N and it converted into Z2 M cross M, where N is less than M and K is less than Q. Okay, and have the following properties for a matrix. Say A belongs to ZQM cross N. What is the property it has? That is G inverse of E, okay, had small entries. So as I told you that the problem here, what was the problem I was having? This C1 into E, correct? So C1 may be having very large numbers. So I wanted to uh, bound it, correct? So what I am introducing, I am introducing a gadget matrix. And the first property of a gadget matrix, if you do G inverse of A, it should have small entries. That means, do you observe what we are going to do? At the place of A, we are going to put our C1. So then we will be sure that this will have small entries. And the second property is this: if G inverse E is multiplied with G, then you'll get back your E. These are the two properties this gadget matrix will have. Okay, now let us see. So the way this is used in GSW is by letting G be a matrix, with every column containing the powers of 2. Powers of 2. Okay, and G inverse the transformation that turns a matrix into a larger one. With every element in its binary representation. With every element in its binary representation. Okay, so in short, what happens actually, suppose I am having a element k, which is an integer, I can convert it into the bit form, correct? It will be having 1010 something like form. Okay, now if I want to get back to the message key, I have to take the inverse of this. This is what your gadget matrix is actually doing. for every element. Your See, what is your gadget matrix? It is a matrix having see powers of 2, 1, 2, 2 square and so on. This is your having your gadget matrix like this, correct? So in short, if you take G inverse, that means I am coming back to my message, back to my vector, say key1, key2 and key n. So if this is the message, if I am multiplying G with it, then I will get back to this gadget matrix, correct? And if I am multiplying G inverse, then it is making it shorter like this form. Okay, so let me just write that. So if you multiply this larger matrix, yeah, as you just read it, what happens, the way this is used in GSW is letting G be a matrix with every column containing the powers of 2. Okay, and G inverse, the transformation that turns a matrix into a larger one with every element in its binary representation form. What G inverse do, it makes the binary representation. Okay, so if you multiply this larger matrix with G, the original matrix is obtained. Obtained. So if you want to see more formally, let us now observe. Suppose we are having two vectors. Let A and A dash. I'm going to write vector as this cap. B vectors in ZQM. Okay. For integers Q and M. That means you can consider this E dash E cap as the binary representation of Q, M as the and E dash cap as binary representation of M. Okay, and let L is equal to say bit length log Q the base 2 plus 1 and what is your N? N is M into L. That is the number of bit needed, number of bit needed to represent an element, in ZQ. These are the bit needed to represent an element in ZQ, and ZQ and a complete vector in ZQM. Respectively. That means if you want to represent anything, a number of bit required for this is in ZQ and this much in ZQ raised to M. It will be multiplied with M. Just it is just saying the bit length of that. Yeah. So what is bit decomposition of this E? vector A, it was in Q, correct? It was of the integer Q, so it has L size. It will be A10 up to A1 L minus 1, then A20, and same it will go up to AM L minus 1. So this is what your bit decomposition of E cap is. Okay. And if you want to see bit decomposition inverse of say B, it will be what? Summation of B1J, comma, your J is running from 0 to L minus 1, and it will be going up to summation J equal to 0 to L minus 1 BMJ. Okay. This is how get the value of bit inverse. So what is actually G inverse? What G inverse does? G inverse is bit decomposition, and to apply bit decomposition, one can multiply matrix G that contains powers of 2. That means this bit decomposition of E cap, this is what your G inverse is. As I told you, G inverse decomposes your numbers, and what happens in your G, that is this is bit decomposition inverse is your same as your G. So if you earlier look at this, it has large size, but if you multiply with G, it will restrict, it will come down, correct? So now we have a tool to form a FHE. Let us start. Now we have the tools to define the scheme. Let chi, as usual, be a B-bounded distribution. Okay, and we consider the message M, which belongs to 0, 1. Okay, now let us start. First is key generation. In the case of key generation, choose a vector T which is of the size which belongs to ZQ n minus 1. It is having n minus 1 coordinate, and set S is equal to minus T comma 1. So it is having, it belongs to ZQN. Okay. What else? Sample uniformly matrix B. Sample formally matrix B from your distribution. Okay. and the size of B will be ZQ M cross N minus 1. And your E, a matrix from yes. So I am sampling two matrices B and E from your distribution carriage to N. Okay, and set B. Actually, E is just a vector. I'm sorry about this. This E is sampled from this carriage to M. Okay, yeah, and set small b is equal to B into T plus E. Okay, and what is your A is of this form, B and small b. Note that if you multiply AS, that should be equal to E. You can quickly check. See, what is your A? It is B, B, and what is your S? It is minus T comma 1. So it is minus BT. Correct? Minus T comma 1. Yeah, minus BT plus B. But what is the value of small b? It is minus BT plus BT plus E. So I'm having E. Okay. Now output. What is the output I'm having? That is our secret key and public key. What is my secret key? What is my public key? Your secret key is small s and your public key is the set A. This is your public key and the small s, whatever it was. Correct, minus T comma 1. That is your secret key. Okay, the first part is done. Now let us go to encryption. How do you encrypt? So encryption of a message M with the public key PK. Again, sample uniformly a vector R which has element 0, 1, M cross M, and set is your ciphertext C. C is equal to RA plus MG. This is your ciphertext. And output your C. This is the ciphertext. What I am doing, I am sampling a R and just multiplying with my public key A and plus add it with M into public vector, public matrix. Gadget matrix is public. See, G is also publicly available. If you observe this G, it was not having a square. That is number of rows and number of column were not same, correct? So yeah, the inverse is actually just bit decomposition of that, so that is not a problem here. This is encryption. And what about decryption? How do we decrypt? Decryption, I need my secret key and the ciphertext. So ciphertext and our secret key. These are the two things required. First, define a W. Define a W, a vector, which is equal to say 0, 0, and the last one is q by 2. Greatest integer of q by 2. This is what I am having. Transpose. Okay, the size is ZQ. And compute mu. What is mu? It is inner product of CS comma G inverse of W. Okay, And what is the output? Output means your message should occur here. Okay, so you'll get your message M. You just have to take the greatest integer of mu upon this q by 2. That will give you a message. Now let us quickly observe the correctness. What is happening here? Suppose this inner product I am just taking as a dot product. So it is CS multiplied with G inverse W. What can you say about this CS? What is the value of C? This is RA plus MG. This is your C multiplied with S into G inverse W. Okay, so if it will be multiplied with RA S into G inverse W, plus the next term will be MS. It will be actually MG S G inverse W, something like this. Observe one thing here, I am having E into S. I told you E into S is E. Look at this, I told you here E into S is E. So this part is what? R into E into, so this is actually just an error, so I'll put it as a E plus some E dash, you can say, plus this is what I'm having, MG S G inverse W. Here also actually there is a problem, I think. I say this part G inverse W should be in the left, otherwise this multiplication won't be possible. Yeah, this should be multiplied left. You do one thing, or you just multiply C into S. Yeah, S in this will be S into C. If this is S into C, then I think it will work. This should be S into C. S is here, so S is here. I'm having, forget about this S. Here I'm having this S here. I'll be having SMG into G inverse of W. Yeah, and by the property of your gadget matrix, the G inverse E into G is same as E, which is same as G into G inverse of A. So this should be your W. This part should be your W. So we are having some error, plus this will be M into, no, sorry, this is SM. SM into this S won't be here. This will be just W. Okay. And what do you know about W? It is everybody is 0 and the last coordinate is q by 2. So this will become actually, and what is your S? This S will go away or not? S is minus t comma 1. Huh. So what is your S actually? It is minus t comma 1, and you have to multiply your message and then W. W is what? This guy. Everybody is 0 and last term is q by 2, something like this. So what happened? This minus 2 everybody will be multiplied with 0, then it will go away. You will be remaining only with m into q by 2. This is the only two things which we are remaining with. At last what I have to do, I have to divide with this q by 2 and I'll get my message. Plus some error is also there. So that's why you just take integer part, greatest integer part. So do you see, in the case of decryption, your message m is equal to greatest integer part of mu upon q by 2, and that's it. You'll get the message. I'll just quickly repeat here what I am doing. In the case of decryption, I'll just net product of s into c, g inverse of w. So this is s into c, g inverse of w. I'm having, I put the value of c, ra plus mg, g inverse of w. If you multiply the first part, this a, s into a or a into s. This part will be having e only. Actually, yeah, the thing is that this is inner product now. So order may be decided later on. I had just written this order, even I should have taken G inverse W. The order, see, that's why they have given purposely as a inner product. Yeah. So this was not a problem that your should be actually, that is okay if it is C into S. That is not a problem. Since it is a inner product, I'll just tell you, this guy can be written as G inverse W multiplied by CS. Yes. And then everything will work. Everything will work properly. That's why they have given this inner product. And you can do one thing, you without opening the inner product. Let us try to do that. Without opening the inner product, let us try to solve. So what is this CS? The value of C is RA plus MG. So this will be RA plus MG multiplied with S, comma, this is G inverse of W. As it is, I am keeping. The next part, what it will be, this is RAS plus MGS, comma, this is G inverse of W again. So RAS, this is what, E into S, this will be error, so it will be some E plus MGS, comma, G inverse of W. This is what I am having. See, this was the problem which I was facing, my error term. Now what I can do, I can write this inner product as G inverse W multiplied with this guy, your error plus MGS. So this will be, first thing is E multiplied with G inverse of W, that will be again an error only, plus I'll be having this M can be outside because M is just a bit. I'll be having G inverse of W multiplied with G into S. So let me call it as some E dash plus, I'll be having G inverse of W as G. So this is M into W into S. So this will be equal to E dash plus, as I told you, this part will be M into Q by 2. So to decrypt, I just have to divide by Q by 2 and take the greatest integer of that. We will get the message M. This is your value of mu. So that's why actually the main aim is uh, you can appropriately define your inner product, which one just by looking at the terms, so that everything goes proper and all the multiplication goes well. Just that's what you have to see. Even if we had done directly G inverse of W multiplied, if this was here, then also there was a no problem in this case. Yeah, if you directly multiply, then also there is not at all issue. This would be the perfect one. You just write E plus mgs multiplied with G inverse of W. So it will be again the first another error plus mg, and this is S G inverse of W, which is E dash plus M. It will be SW. And what is the value of SW? It is your Q by 2, M into Q by 2. This works now. This is perfectly fine. Yeah, so I'm having my decryption is this, and for addition and multiplication evaluation, eval add, that is C add, it is just add the cipher text C1 plus C2. Okay, and if you want to do eval multiplication, what you have to do, C multi is what? It is C1 G inverse C2. This is how the multiplication works here. C1 G inverse C2. And you can check the decryption, check the decryption actually. You just multiply with the secret key and you'll find it. Mostly if you observe, the main decryption is just multiply with your secret key with the C. You just C multiply with your secret key. And then you just have to divide it with this J inverse W and get the final answer. Main rule is main your decryption is this CS. Sometimes S into C, in some book you will find S into C. So as per the order you can decide. That's not an issue. So yes, we got a FHE scheme which is working well. Now we have to make it a multi-key FHE scheme. Okay, so in the multi-key FHE scheme, as I told you, we there are n parties, each having their secret key and public key pair. Okay, yeah, multi-key FHE scheme we'll do in the next class.